Good evening, students. Prishis are back with a new topic, this time in rolling body. So, see the topic, important rolling body problem. I'll give a few lectures on this. This is lecture 1. This is my credential. So, what I'm discussing now, I'm giving you in the diagram. This is a massless inextensible string 1, wound around a uniform disk. This is the disk, uniform disk. Okay. And uniform disk is a pulley, but shape of a disk, uniform disk shape pulley, this one. And this other end is attached to the rigid roof. Just see this is the roof. Okay. Another string 2, this is string 2, is wound around the pulley. This is like this. So this is wound like this. Okay. And supports a block of mass M2. The string is wound like this and supports a block M2. This is also massless inextensible string. Okay. Mass of the pulley is M1 and this hanging block is M2. Radius of the pulleys R. The second pulley, past pulley, both of them are massless inextensible pulleys. So this radius is capital R. Assume no slipping of the strings on the pulley surface. कोई slipping नहीं है. So this will unwind because we pull down, so this will unwind. Okay, this string, this mass will come down, this will unwind, and this will also come down along the string 1. That disc also will come down along the string 1. Okay. So we question क्या है भाई? Acceleration of the block. ये block का acceleration कितना है और ये pulley का भी acceleration कितना है? टेंशन इन द स्ट्रिंग 1 एंड स्ट्रिंग 2, इस दोनों में टेंशन कितना है? बस दोनों का ये पुली और M2 का एक्सीलरेशन एंड स्ट्रिंग 1 स्ट्रिंग 2 में टेंशन इज द वी हैव टू फाइंड. सॉल्यूशन देखते हैं. पहले हम लोग इसको आई डोंट अटैच दिस स्ट्रिंग टू दिस पुली. सो हाउ द डायग्राम विल बी. So like this, let's first calculate the acceleration of the point P. This is the point P, this point P. Okay, in the pulley. Let's first calculate the acceleration of the point P in the pulley. A figure there, figure 2. So उसके लिए free body diagram I have drawn it. This is the pulley, a bigger size. This is the P point. This is the tension T1. I have shifted it to the center of mass C. C and O are same point. O is the geometrical center. C is the center of mass. Since it's a uniform disk, so O and C are same point. So if I'm shifting T1 to the center of mass, then the torque due to T1 around center of mass also I have to show. This is the torque. This torque I have shown here. This is the torque. This is the alpha. Okay. So since the pulley is uniform, so geometric center and the center of mass, they match. Okay. So in this figure 3, what we have shown, the net force passing through the center of mass and the torque due to all the forces about center of mass is shown. So I have shifted all forces to the center of mass, and while shifting the torque due to all forces about center of mass also I have written. That is only one force T1 shifted to center of mass and T1R clockwise shifted around center of mass. This is a theorem. Any number of forces acting on a rigid body can be replaced by a single net force at center of mass and a single net torque about center of mass. That net torque will be in sum of individual torques of all the forces about center of mass. This is what I am using. This is a very extremely useful, I think most useful theorem in rigid body. Okay, any number of forces I can simply write as a resultant of all those forces at center of mass, but that's not sufficient. The torque of each individual force about center of mass I vector R and write a single torque about center of mass. So any number of forces can be replaced by a single net force and a single net torque about center of mass. This is a theorem. So the figure 3, the net force I have shown passing to the center of mass mg and T1, but T1 was acting here, so was shifted here. So the corresponding torque due to T1 about center of mass T1R I have shown in clockwise manner. So alpha becomes clockwise. So let's write the Newton's law. Net force in downward direction m1g minus T minus T1, that is m1 into C downward, m1 into AC downward. AC is downward. I have shown it AC. So m1g minus T1 is equal to m1 AC. So similarly, torque will be about center of mass T1R will be ICZ. CZ means the axis passing to center of mass. So ICZ, the moment of inertia about line CZ, and alpha. So T1 into R is ICZ into alpha. Question 2. Since the string is inextensible and remains taut, so obviously this point A has a zero velocity. This is part of the static string. So the disk rolls without slipping along the string because there is no slipping already given. So since the string is inextensible and remains taut, point A has zero velocity and the pulley rolls down without slipping on the string. So that means AC or AO, जो भी बोलो, the same point is equal to alpha R rolling without slipping. Alpha is the angular acceleration. Okay. So this is the equation number 3. So 1, 2, 3. तीनों से हम solve करेंगे. So solve कैसे करेंगे? That is AO and AC is equal to alpha, that is AC is m1g by the solve karo usko. You can remove R to the right hand side and alpha is AC by R. So this becomes ICZ AC by R square. So after that you can R. So you get m1g is equal to AC into m1 plus ICZ by R square. Just adding this you can get. So what is AC? m1g by m1 plus ICZ by R square. So m1g by m1 plus m1g by m1 plus ICZ by R square. So ICZ is half m1 R square. So R square cancel. So this becomes 2g by 3. So we got the acceleration of this point as 2g by 3 AC. And tension we are finding from this mg minus mac here from here. T1 will be m1g minus m1 AC. So we just write that. This is m1g minus m1 AC. So m1g by 3. Yes or no? So this is the tension. And tangential acceleration of P with respect to O will be how much? Is of point P here with respect to O, how much? With respect to O, what is that? Tangential acceleration of P? Alpha R in downward direction. Okay, alpha in downward direction. The tangential acceleration of P with respect to A कितना होगा ये P with respect to A is this point, P with respect to A, that is P with respect to O and O with respect to A. Acceleration of O with respect to A is alpha, that is 2g by 3 downward, and tangent acceleration of acceleration of P with respect to O is also alpha. Just see here, this is the point A. Let me write this is the point A, of course. See the above diagram. This is the point A. With respect to A, C is rolling without slipping along the string. So acceleration of C with respect to A is alpha r, and acceleration of P with respect to C is also alpha r downward. So acceleration of P with respect to A will be acceleration of O with respect to A plus acceleration of P with respect to O. So that is 2 alpha. Or you can just take this is the axis of rotation. So this is 2r. So alpha into 2r is the acceleration of P with respect to A. A is the point fixed to the string, that is fixed to the ground. So then I got 2 alpha is the acceleration of P with respect to A. So that is 2 A naught 2g by 3, that is 4g by 3. So this acceleration is 2g by 3. C ka acceleration and P ka acceleration downward will be 4g by 3, which is greater than g. So this is the key point here. P is 4g by, the acceleration of point P is 4g by 3 downward, which is greater than the maximum tangential acceleration of the block, which is g. Suppose I hang a block here now. I hang a string block here. What the maximum acceleration of block will be? Under gravity, maximum will be g. Understood this or not? This, because this is mg and tension upward. So maximum acceleration will be, if tension even 0 also, it will become g only. So, but this point P's acceleration how much? 4g by 3. And string's acceleration how much? This is 4g by 3. This is g only. So this is coming with a bigger acceleration downward. So this string will become loose. So that's what I wrote. The tangential P with respect to A is 4g by 3. Now if we hang a block at the point P with help of a string, the maximum acceleration of the block will be g downward when there is 0 tension in the string. If tension is there in this string, then it will be still less than g. So while the acceleration of point P is 4g by 3. Yes or no? Without that new string also it is 4g by 3. It can be more than that. In other words, P will be coming faster than the block going down. So obviously the string connecting the P2 block, this point P to the block, this is moving faster than this one. So this string between P to that block M2 will become loose. Okay? That's what I wrote. P is 4g by 3 and the hanging block will be less than, the maximum will be g, will be less than g. So the string supporting the hanging block will become loose and the tension T2 in the string is 0. So therefore, what is acceleration? If string become tension 0, then block actually be g downward. That's what. Therefore, this block and the supporting string has no effect on the motion of the pulley. So the acceleration of the pulley is 2g by 3 and tension is m1g by 3. I have already discussed and in figure 2. So the block has the free fall with acceleration g downward and T2 equal to 0. Very simple. Even if you calculate it by taking T2 and all this, T2 and all, writing the basic dynamic equation of the rigid body, you will find that T2 is negative. That means negative tension not possible, so it will be 0. That's what I am writing here also. We could have solved this problem by assuming some tension T2 in the string 2 and solving for T2. T2 will come out negative, implying the string becomes loose and the T2 is equal to 0. So negative value of tension not acceptable. Kyun? Not actually for an inextensible string, because string cannot withstand compression. Okay. Once you try to compress it, it becomes loose. It cannot withstand the compression. Yes or no? So it's a very simple way of solving this. Otherwise, if you take the T2, here what I wrote, it could have solved this. This will be quite long. These type of questions are quite common in examination, and this consumes a lot of your time. So now you see that you can simply ignore the block and the string. Similarly, another question प्रॉब्लम मैं आपको डिस्कशन करूं आपके साथ. ये एक प्लांक है placed on a smooth ground, and there is a cylinder. On the cylinder top point, a cylinder, there is a string wrapped around cylinder and connected horizontally to the rigid wall. The top point is P. This is mass of the M. Mass of the plank is MP. C is the center of the cylinder. The central axis, the center of mass of the cylinder lying on the central axis. This is disc or cylinder, whatever called same. Okay, the plank is pulled to the right with an external force capital F, as you see. So what are the forces on this thing? This going to, there is friction is there between the disc and the plank. So there is a drag force on the bottom of the disc to the right direction, so small f. So let the tension be T. I don't know how much it is. So in figure 5, this is the situation. So that's what I wrote. Just like the previous example, let us consider the string without this, consider the disc without the string being attached. Let us see what is the acceleration of point P, whether there will be tension in the string or not. That's what my aim is. So this F is here, so I can shift it to the center of mass F, but I have to write the torque due to F also, anti-clockwise torque due to this F about C, torque CZ. I just told you this theorem. So now let us write the kinematics. Small f is equal to m into AC. Okay. Or AC bar is F by M, I cap. Torque CZ is ICZ into alpha. That will be this is the alpha. Angular acceleration. And FR, F into R is the torque. Yes or no? That is ICZ alpha. And alpha is FR by ICZ. Torque CZ is ICZ alpha. FR is ICZ, FR torque CZ is F into R in this anti-clockwise manner, that is ICZ into alpha. F into R, the C. Which direction? Anti-clockwise. Torque. What to write? Write this torque as FR in this. Right. This is what I wrote. So alpha is how much? FR by ICZ. Okay. So am I clear? So what is AP with respect to C? Alpha into R. This is R. So with respect to C, this is purely rotating. So this tangential acceleration of P with respect to C will be alpha R to the left. This is, and alpha is FR by ICZ, so FR square by ICZ minus I cap. That's very simple. That is P, acceleration of P with respect to C in left, minus I cap is towards left. But C itself is traveling to the right, actually to the right. That I have to find out how much. Okay. S is F by M I cap, already in equation 7 I have written that. That's what I wrote here. A P with respect to ground, then how much? A PC plus a CG. A PC again I am saying PC is minus alpha r I cap. Okay, that is fr square by Cz minus I cap, and Scz is how much? Small f by m, equation 7, you see f small f by m, small f by capital M is ACG, that is the I cap direction plus I cap direction. So APC plus ACG is f common r square by Cz minus I cap plus 1 by m plus I cap. That is AP with respect to ground. A topmost point with respect to ground is this much. Let us see that value. Okay. So ICZ is half mr square. So half mr square here cancels. So 2 by m minus I cap and plus 1 by m I cap. So that is minus f by m I cap. F by m minus I cap. So APG is to the left. So acceleration of point P is to the left. If it acceleration of point to the left, so this string will become loose. Yes or no? So this tension which are shown here will be becoming 0. Okay, so therefore this string becomes loose, tension becomes 0. So we can easily solve the motion of the disk without taking the string tension. So you see the tension to the left and no longer I am taking. Okay, so now you can now solve it without taking this top tension. So here it is for the Planck, it is f minus small f. This is capital F minus small f is mp into capital A is the acceleration of the Planck. Small f is m into mass of the disk into AC, and fr is I Cz alpha. Okay, acceleration of the disk with respect to the Planck in backward direction how much? This is alpha. Let's find out the acceleration of the disk in with respect to Planck in backward direction. With respect to Planck, the acceleration disk will be in forward direction will be AC minus capital A. Backward direction will be capital A minus AC. Just see this. What is the alpha is in this direction. So I have to take the acceleration of C in this direction with respect to the Planck, because I want to use that rolling without slipping condition. So with relative to the Planck, if I know the acceleration of the disk to the left, then that I can equate to alpha r. So what is the acceleration of the disk with respect to Planck in the backward direction? So acceleration is AC and this is capital A. So acceleration C with respect to Planck will be AC minus capital A in forward direction. So in backward direction will be capital A minus AC. So that must be equal to alpha r for rolling without slipping. Okay. That is, I will write for rolling without sleeping. Now, after that you solve these equations. Very simple, you can solve this equation. F minus f by mp is A, put it here. AC, f small f by m, and alpha r, alpha is fr square by Cz into r, fr square Cz. So you get solving this 2f by m. So small f will become that way, f by 1 plus 3 mp by m. So AC will be from the same equation, you will be getting f by m. Okay, that is clear. So then a capital A also f minus small f by mp, you can get this. So this is the thing. So now the main point of these two questions is that sometimes the tension is not there, but if you want to take tension, that will make it very long. So first I proven that the tension is not there, so I don't have to bother about it. So how to know tension is not there? If the P is moving toward the support, then the string becomes loose. Okay. Later we will discuss that this is the center of this above center of percussion. That's why this is moving to the left. We'll see that next class. Next class I will go to a different situation. That is lecture 2. So today I think you have all understood this. This is a very, very important point to note. So it will simplify your questions in your It will simplify your question. Simplify your solution to this type of question. So you will be very confident. You will definitely will be able to solve it easily. So thank you all. Have a good day.